Hello and welcome to lecture 56. We are discussing about the Turboshaft engine. In last lecture, we started discussion on introduction to Turboshaft engine, where we have found this Turboshaft engines for aerospace application. Mainly it is focused on application for the helicopters. Then we were discussing about various other applications of this Turboshaft engine, which includes for the marine purpose, that is what is used for the power generation purpose, that is what is also been used for say future UAVs or already existing UAVs. So, that is what is of major focus of applications. Then we were discussing about the advantages of this Turboshaft engine and what are the reasons why we are having say focus on the development and research activities for the Turboshaft engines. There are challenges for the Turboshaft engine and we have focused on those challenges also. Now, let us move forward with say kind of configurations or the type of say Turboshaft engines which are possible with. So, here in this case if we look at carefully, say we are having this as our say Turboshaft engine, where we have compressor that will be followed by the combustion chamber. We have our turbine, that is what we say as a HP turbine, and we have the other set of turbine blades, they are called power turbine, and we have exhaust. So, here in this case if we look at carefully, say this HP turbine, that is what is used to rotate the compressor, and this power turbine it is used to rotate the shaft. So, we can say this configuration as say single spool Turboshaft engine. Similarly, here in this case if we look at, we have the construction, that is what is slightly different. If we look at carefully, the exhaust which is coming out from the compressor, that is what is been supplied to say recuperator. So, if you recall, we have discussed this kind of configuration for the turbofan engine. Even we have discussed such kind of configuration for turboprop engine. Okay. So, here the whole purpose is to say reheat the air which is going inside the combustion chamber, and by doing so the fuel efficiency that can be increased. So, if you recall in last lecture we were discussing for the application of tanks, military tanks, where the focus is on say fuel economy, where people they are using this kind of configuration. Okay. Now, let us move towards the other possible configuration. So, here in this case it says booster on HP spool. Here the initial stage, as we have discussed earlier also, they are named as say LP compressor or the booster compressor. Later part, that is what is defined as a maybe compressor or HP compressor. Here in this case if we look at this HP turbine, that is what is used to rotate both the compressor stages, and our LP turbine, that is what is connected with the shaft. So, this we are having the configuration, we can say it is a two spool configuration. Say one spool, that is what is dedicatedly been connected with the gas turbine, and other spool, that is what is connected with the shaft. In line to that, there is other possibility also. Here if we look at, the construction is different. Just look at the construction, what is happening here. Here in this case if we look at, we are having compressor or we can say HP compressor, that is what is been rotated by HP turbine, and in this case if we look at say this LP turbine, that is what is connected with the compressor as well as the power shaft. So, based on the requirement, based on the construction of the engine, and as per the design, these different configurations are possible with. You also can make your engine with your understanding. There are possibilities, there are different applications of these engines, and based on the applications people they are configuring these engines. So, what all we are discussing, they all are the existing engines. Okay. Now, let us look at the other kind of configuration. So, here in this case it says double booster on HP spool. So, rather saying say compressor, they say both the compressor we have booster as well as HP compressor, they are being connected on say HP turbine. So, this is what is my HP spool we can say, and here in this case if we look at carefully, say my LP turbine, that is what is connected with the power shaft, and here we are having the exhaust. Okay. Similarly, here in this case if we look at, it says we are having this double booster, that is what is on say LP turbine. So, LP turbine, that is what is used to rotate this double booster as well as this shaft, and that is what is generating the power to rotate both compressor as well as for the rotation of our shaft. Okay. So, here also if you look at carefully, we are having this as our exhaust. I am specifying again and again because we want to differentiate our turboprop engine with turboshaft engine, else you will be having understanding this both the engines are same. What is the difference? So, difference is in terms of construction and in terms of purpose. For propeller engine, we may be using our exhaust nozzle for the generation of thrust. Here in this case, our expectation is not to generate the thrust. Okay. So, just observe the things carefully. Okay. It seems simple, you can go with say line diagram, just try to do practice for plotting this kind of diagrams. So, that will give the confidence in terms of your understanding as well as maturity. Now, let us look at this is what is say 2 spool kind of configuration, rather we can say it is 3 spool configuration. What is the reason? Here in this case if we look at my HP turbine, that is what is connected with the HP compressor. My LP turbine we can say that is what is connected with my LP compressor, and we are having the free turbine. This free turbine, that is what is connected with the shaft, and that is what is used for the rotation of our say rotor for the helicopter, or maybe that is what is connected with the shaft in order to move say your propeller for the marine application. So, there are different possibilities. This can be connected with the motion as per our requirement with the vehicle. Suppose if we are talking about application with the tanks. So, there are different possibilities what all we are discussing at this moment. Now, let us try to understand say the configuration here. We can say it is a single spool configuration. You can also say that as a 2 spool configuration. The reason is say here in this case we have our HP turbine, that is what is connected with this compressor. We can say that as a 1 spool, and on the rear side we are having this turbine, we can say it is a power turbine or free turbine, that is what is connected with the load, or that is what is connected with the rotor, and here we are having the exhaust. So, these are the stations, say for the sake of brevity, sake for understanding, and in order to go with the cycle analysis, we will say this as a upstream condition. This is at the entry of my compressor. This represent the exit of the compressor, entry of the turbine, exit of the turbine, we can say it is HP turbine. Similarly, this is what is the exit of your power turbine. These are the engines, we can say Safran, Ardiden, that is what is this kind of configuration. Here in this case if we look at carefully, this is what is representing the intake. This is our say centrifugal compressor that will be connected with the other stage of centrifugal compressor. We have reversible combustor that supplies this flue gas to the turbine. This turbine, that is what will be rotating these 2 centrifugal compressor, and on the rear side we are having say power turbine, that is what is connected with the common shaft. Similarly, here in this case we are having Safran engine. So, there are different engine manufacturing companies, they are making different kinds of engine with different kind of possibilities. So, here it says like you are having say axial flow compressor, we can go with the centrifugal compressor also. Here if you look at, we are having the combination of axial centrifugal compressor, then we have discussed we are having single can combustor, that is what is used to rotate the shaft. So, there are different possibilities, based on the understanding, based on the requirement, you also can make your own configuration, you can design your engine. Okay. Now, let us try to analyze this engine. Let us focus on the intake. We can say this is representing TS diagram, and this process from infinity to 2, that is what is representing actual process, that is what is happening inside my intake. For this intake, what all information we have is we have our diffuser efficiency. From that diffuser efficiency, we can calculate what will be the inlet total pressure. Okay. We can calculate what will be the inlet temperature at the entry of our compressor, or we can say intake exit pressure. So, let us look at this is what is giving us idea in terms of calculating say total pressure and total temperature at the entry of the compressor or at the exit of our intake. Now, let us look at the next component we have. The next component we have is our HP compressor. This HP compressor or the simple compressor, we have information about the pressure ratio. We also have information about the efficiency. If we are having say multiple compressors, say axial compressor, that will be followed by the centrifugal compressor, there we will be having the polytropic efficiency, which will be coming into the picture. So, under that configuration, we can calculate what will be our efficiency, and based on that we will try to calculate what will be the exit temperature from this compressor. So, now we have information about point 3, we can say it is T03. So, we have reached here. The next component what we have is our combustion chamber, and in combustion chamber we have realized there will be drop of pressure, and that drop of pressure we are representing in terms of P04 here. What is happening here in our combustion chamber? In order to analyze that, we will be going with say our control volume approach. This is representing the energy input to the combustion chamber. We can say it is m dot infinity into H03, amount of fuel what we are adding into calorific value and combustion chamber efficiency, that is what is representing the amount of heat input, and this is representing the flow which is coming out. It says m dot infinity into mf into this will be the temperature. We can say this is the temperature with which the flue gas that will be entering inside the turbine, and this we also can say is representing turbine entry temperature. So, based on that we will try to calculate what will be the fuel air ratio, that is what is required, or amount of fuel what we need to add in order to achieve this temperature T04. Okay. So, this will be giving us idea in terms of fuel air ratio for the combustion chamber. Now, what next component we have is our HP turbine. So, for HP turbine what all information we have? Basically this HP turbine, that is what is used to rotate the compressor. So, what we will be doing? We will be balancing the work. This is a work balance of HP turbine and what we say as HP compressor or the compressor. This work we can represent as say MCP delta T0, it is m dot infinity, okay, and here it is T03 minus T02, that is what is representing the compressor work, and 1 plus FCP delta T0, that is what is representing our turbine work. From both the side m infinity, that is what is going out. We are cancelling that part. Based on this, we can calculate what will be the temperature at the exit of our HP turbine. And in order to calculate what will be the pressure, we have our information about the efficiency of this HP turbine, and that is what will be helpful to us in order to calculate what will be the pressure and what will be the temperature at the exit of HP turbine. Now, here let me put the point. Next component what we have is our free turbine. So, let us try to understand this free turbine. This analysis is different from what all engines we have discussed till now. Let it be say turbojet engine, turbofan engine, or maybe turboprop engine. What was our requirement? Our requirement was mainly in order to have the thrust as well as power. Suppose if I am talking about the turboprop engine, if I am talking about say turbofan engine, the whole purpose is to generate the thrust. That's the reason why nozzle is coming into the picture. If I am talking about say turbojet engine, there also our purpose is to generate the thrust, and that's where you need to have the nozzle. Say here my purpose is not to generate the thrust, so we will try to extract all energy possible by using this turbine. Okay, and that's the reason why this line, if you look at this process of expansion from 5 to 6, that's what is representing the free turbine expansion. Okay, we will be having exhaust that will be coming out at temperature. The temperature is higher than that of the entry temperature, but we will try to extract maximum amount of power by using this free turbine. Okay, so it says for maximum total power recovery, we need to go with the efficiency term. That efficiency term we are correlating in terms of pressure ratio, and if we are rearranging this efficiency term, we will be able to calculate what will be the exit say temperature from this. Now this pressure, that's what is tricky business, as we are not using the nozzle. This is just say duct which is exhausting. So that's the reason why our criteria for critical pressure that will not be coming into the picture. We can say exhaust pressure is atmospheric pressure. That's why this pressure we are putting as T6, and temperature we are putting as a T6, and pressure we are putting as a P6. Now once we have this information, if you recall in our second week we have discussed, this is representing our propeller engine and this is representing our turboshaft engine, and here both the turbines we have defined as a power turbine. The purpose of power turbine for our prop engine or turboprop engine is to rotate the propeller, and here in this case this is connected with the gearbox, bevel gear, that's what is giving say power to the helicopter rotor. So under that condition, power delivered to the free turbine, power delivered to the load, and thermal efficiency, they will become our performance parameters. So let's try to look at what we mean by power delivered by the free turbine. That's what we can write down in terms of m dot into 1 plus f Cp delta T0. Here this delta T0 is T05 minus T6. Similarly, we have certain mechanical losses which are happening because it's a power transmission. So at the load or at the shaft we will be having power. That's what is calculated based on mechanical efficiency. Now thermal efficiency, that's what is very important term because that's what is related with the performance calculation. As per the report by pre-release, it says my thermal efficiency, that's what can be represented by expansion work minus compression work divided by the amount of heat what we are inputting. Basically this is nothing but we can say it's output by input. Suppose if I consider say my power shaft and my compressor shaft, they both are same, we can write down this equation. When we are having the free turbine as a configuration, that time we need to write down that as a shaft power divided by mf into qr. Basically we are interested in what is the efficiency, thermal efficiency of this engine. The other parameter which is of our interest is a specific fuel consumption. Basically since this is what is with the shaft power, and that's the reason why we are writing that as a brake specific fuel consumption. Be careful, this has nothing to do with the thrust, it is mainly with the power, and that's the reason why it is called brake specific fuel consumption. And this brake specific fuel consumption, it is written as m dot f divided by your shaft power. Suppose if it is thrust, we know that's what is given by m dot f divided by thrust, but this engine is not generating thrust, this engine is generating power, and that's the reason why we are writing is m dot f divided by shaft power. Now, let us take one numerical, that is what will be building the confidence in terms of doing the cycle analysis for say Turboshaft engine. Let us consider say heavy duty Turboshaft engine, that is what is having say flying Mach number of 0.21 at the altitude, where pressure and temperature are say 51 kilopascal and 252 Kelvin. The engine core mass flow rate is say 12 kg per second. Maximum turbine entry temperature is 1320 Kelvin. The compressor pressure ratio is 9.5. There is a drop of pressure which is happening in combustion chamber, it is say 2%, and different efficiency values are given. Say diffuser efficiency is 92%, compressor efficiency is 84%, burner efficiency 98%, calorific value is 44 megajoule per kg, and the turbine efficiency they are 88%, considering say mechanical efficiency of 99%. The value of Cp for air it is 1.005 kilojoule per Kelvin. Cp value for the hot gas is 1.154 kilojoule per kg Kelvin. The gamma value we are considering as 1.4, and here in this case for the hot gas it is 1.33. Let me bring the observation here. If you look at this compressor efficiency, it is 84%. So, you can imagine what all engines we were discussing, say turbojet engine, say maybe for turbofan engine, for turboprop engine, this efficiency value was higher. Now, for this kind of engines where we are having say combination of the engine where the efficiency is slightly on the lower side. Similarly, if you look at for the turbine also, it is 88%. So, just observe these things carefully. Okay. Now, let us try to analyze this part. We will be discussing how do we solve this numerical. So, initially we have our intake, and for this intake my flying Mach number, temperature, pressure and diffuser efficiency is given. We can calculate what will be the exit temperature and exit pressure from the intake. We have our next process, it is a compression process. For this compressor efficiency is given, your pressure ratio is given, gamma value is given. So, we can calculate what will be the total temperature and total pressure from the exit of our compressor. We have our component, that is what is say combustion chamber. For this combustion chamber, the efficiency, total pressure loss, turbine entry temperature, calorific value, these numbers are given to us. So, we can calculate what will be the outlet pressure and fuel air ratio from the combustion chamber. We have our component, that is what is say HP turbine. For this HP turbine, we have efficiency, we have turbine entry temperature, we have this efficiency and Cp value. We can calculate what will be say outlet pressure and outlet temperature from the HP turbine. Now, till here the all calculation method seems to be similar. Now, we have our next component, it is a free turbine, and for free turbine we have efficiency, that is what is given. We can calculate what will be the exit temperature and what will be the exit pressure. Exit pressure we are considering, that is what is say atmospheric pressure. We are considering perfect expansion, that is what is happening, and based on that we can calculate what will be the performance parameters. So, this is how we will be solving the numerical. So, we need to understand what is a construction based on the information, that is what is given. If you are making mistake in terms of understanding the information given, you may lead with some wrong kind of calculation, you will be coming out with some different kind of cycle. So, be careful what information, that is what is given to you. Here in this case, suppose if I consider rather having free turbine, if it is having say gas generator, that means I will be having this HP turbine and free turbine, they both will be same. So, be careful in terms of doing the calculation, in terms of understanding the things. Okay. Let us look at, suppose say we are having first component, it is say intake. For that flying Mach number is given, it is 0.21. Temperature and pressure they are given, it is 252 Kelvin and pressure is 51 kilopascal. diffuser efficiency is 92%. So, we can calculate based on that what will be our outlet total pressure, and this pressure is coming to be 52.46 kilopascal. Similarly, we can calculate the outlet temperature. This outlet temperature, it is coming to be 254.2 Kelvin. Okay. So, these are the information that is what is at the entry of our compressor. Let us take the analysis for the compressor. We want to calculate what will be the outlet pressure and what will be the outlet temperature from this compressor. So, when I say outlet pressure, that can be calculated based on what is our compression ratio. For this engine, compression ratio is given, that is 9.5. So, let us put that value. It will give the outlet pressure to be 498.4 kilopascal. Similarly, in order to calculate your temperature, this temperature we are correlating in terms of efficiency as well as what is our say pressure ratio. Here be careful which efficiency is given. This efficiency is the compressor efficiency. So, we will not be bothering of the polytropic efficiency case. So, putting the numbers say 9.5 and 84% efficiency, at the outlet temperature we are getting 527.34 Kelvin. Now, the component we have is combustion chamber, and it says there is a drop of pressure by 2%. So, if we are putting that 2%, the outlet pressure is coming 488.43 kilopascal. Now, in order to calculate say temperature, here in this case turbine entry temperature is already given. In order to achieve this turbine entry temperature, how much amount of fuel we need to add, that is what need to be calculated here. So, in order to do that calculation, we will be putting our energy balance, and from that energy balance we can write down the fuel air ratio. That is what is given by this formulation, where we need to be very careful in terms of putting Cp of hot gas and Cp of cold gas. So, if we will put this number, it says my fuel air ratio, it is coming to be 0.025. Okay. Now, this combustion chamber part it is ready with. Let us move towards the next. What we know, this turbine stage what we have, suppose if I say is a HP turbine, that is what is used to rotate our compressor. So, we will say we will be putting our work balance here. Here in this case we can straightway write down these numbers, and by putting so we will get the outlet temperature from this turbine to be 1088 Kelvin. Okay. Now, let us move towards the calculation for the pressure ratio. Based on this pressure ratio, we can calculate what will be the outlet pressure from the HP turbine. So, we can write down this equation. We have information about say temperature at the entry and temperature at the outlet, and efficiency also is known to us. So, if we will put this value, the outlet pressure, that is what is coming to be say 198.98 kilopascal. So, that will be the pressure with which the flow is coming out from HP turbine. So, temperature is 1088 and the pressure is 198.98 kilopascal. Now, let us try to understand what is our next requirement. We want to go with the calculation for the free turbine. We want to extract maximum amount of work, and in order to calculate that based on the formulation for say free turbine efficiency, we can calculate what will be the temperature at the exit. Since this pressure it is say 51 kilopascal, it is a exit pressure, and entry pressure is 198.98 kilopascal. So, this will lead to give the exit temperature to be 813.55 Kelvin. This number is not a small number, just imagine that part. Okay. So, now let us try to calculate what will be the power delivered by the free turbine. This free turbine power we can say it is given by m dot into 1 plus f Cp delta T0. This delta T0 we will be putting, and by putting say your core mass flow rate of 12 kg per second, fuel air ratio of 0.025, we will get the free turbine power to be 3896 kilowatt. Okay, it's almost 3.89 megawatt. It's a big power or big number. Now we have our mechanical efficiency, that's what has been mentioned for the power turbine, that's what I say 99%. So that's the reason why the power which is available at the shaft, that will be 3.85 megawatt. Okay. So let's move towards the next calculation. It says the calculation of the thermal efficiency. This thermal efficiency, we can say it's given by shaft power divided by what is our MF into calorific value of the fuel. If we are putting our shaft power, that is 3.896 into 10 to the power 6, be careful about the units, divided by, we have our MF value, it is given by 0.025 into 12, calorific value of the fuel is given, it is 44 megajoule per kg. So if we are putting this number, the thermal efficiency is coming to be 29.52%. Now let's do the calculation for the brake specific fuel consumption. This brake specific fuel consumption, it is given by m dot f divided by shaft power. If we are putting this number, it says the brake specific fuel consumption is coming to be 0.077 gram per kilowatt second. Okay. So in overall, if we try to look at, we have information about the flying Mach number to be 0.21, the temperature and pressure at particular altitude, they are 252 Kelvin and pressure it is 51 kilopascal. This engine, that's what is generating say power from the free turbine, it is 3896 kilowatt. The power which will be available for rotation of the say the main rotor of the helicopter, that's what will be around 3857 kilowatt. The efficiency what we have calculated is 29.52%, and brake specific fuel consumption we have calculated, it is 0.077 gram per kilowatt second. Now here also you can do the parametric study. This parametric study, that's what will be focusing on the parameters like change the pressure ratio of the compressor, change the turbine entry temperature, these two variants which are possible with. So with the interest of time and looking to the session for this week to be 5, we will not be discussing about say effect of various parameters on the performance. It is but obvious you can do that part, because for many engines we have discussed that part, how your performance parameters which are varying the performance of this engine, like turbine entry temperature, say your pressure ratio, mass flow rate, those parameters can be studied in order to achieve what will be the shaft power that will be available to us. Okay. So here in this case, this is a straightforward calculation what we have. You can go with the reverse calculation also. You can say this is the power, that's what we are looking for from the shaft. So maybe that load power it is given to you, and from there you need to do your reverse calculation in order to select what need to be the pressure ratio, what need to be the turbine entry temperature. So now I am sure you all are confident enough in order to do this kind of calculations. So here we are stopping with this lecture. In next lecture we will be discussing about the special kind of configuration which is of our more interest. It's a turboprop engine which will be the future coming engine, and we will be discussing the cycle analysis for say turboprop engine, say prop fan engine, and then we will be solving the numerical for that. So here we are stopping with. Thank you very much.